Hello, everyone. This is Dr. Hutchison. So, if you don't know me, I teach this course now, but I also teach the design course ME2761 and Machine Dynamics ME3313. I'm going to be taking over the mechanical portion of this course for the semester. We're going to be doing it all online in accordance with the new campus policy. So I'll be presenting these lectures online. I'll put them on YouTube so you all have access to download them or to view them. I'll also post slides on Canvas along with the quizzes. This week's supposed to be a soft start, so the quiz, if you miss it, it won't be a penalty. Sorry, let me turn my phone off. So anyway, we'll get started today with the lecture. So if you have any problems accessing the lecture or have any questions, let me know. My email's rhutch@mst.edu. All right, let's get started. Okay, today we're going to talk about measurement and inspection. So measuring. Something that's very important in mechanical engineering. When we make parts, we have to know how big they are. We have to have some standard for how big they're supposed to be. And we're interested in the difference between those things. The allowance for how big something can be, the tolerance and how much variation there can be in a part. So we need to define a few things. So measurement, really don't need to define it, but it's the act of measuring some property. Size, which obviously is going to be important in mechanical engineering, measuring the dimensions of things. Temperature, surface roughness, lots of things that you might want to measure. And then there's inspection, which is a feedback mechanism to ensure that once you have manufactured a part, it meets specifications. So in the design phase, you establish the specification, you provide that specification to the manufacturing side, the machinists, they make the part, and then you verify that the part meets the tolerances set forth during the design portion. There's different ways of measuring attributes. So that's something that you use a fixed gauge, which we'll talk about later. Variables, something that could change. You can measure with some kind of a calibrated measuring instrument. We'll talk more about that in a bit. There's different standards for measuring. There's gauge blocks. A gauge block is going to be a precision machine chunk of metal, usually, that will be ground to a very, very precise dimension. You can use it as a go, no-go gauge, which we'll talk about later, or pass-fail. These need to be fairly hard. If they're not hard, then measuring metals with them, you might end up damaging the gauge block and changing its dimensions, and that defeats the whole purpose of having a gauge block. So you could do other fancier materials, carbide ceramics. I have not seen those personally. I'm sure they exist out there. Usually these are hardened steel, very hard steel, like Rockwell C65. That's very, very hard steel. You don't really care about the brittleness from it being that hard for a gauge block. Unless you drop it, then it's going to shatter. So used for different things, laying out things and setting up CNC machines or setting up measurements. Calibrating instruments, that's a very important one. So if you want to calibrate a set of dial calipers, you need a fixed reference. So usually your dial calipers and micrometers will come with some kind of a gauge block for verifying that they're still in spec. And you have to measure the measuring equipment. That's an important thing in quality control, is verifying that your measuring equipment is actually correct. Just a funny anecdote on this. I worked at a company where I was working with a guy whose job was to do this, and they would measure measuring tapes, and it was just kind of a funny thing. But all the measuring tapes had to be calibrated or had to be checked to make sure that they were within specification. All right, gauge blocks. Now all these things are going to expand and contract at temperature. So there's a standard temperature for measurement, and that's going to be the temperature at which the gauge block is going to be at its reported dimension within tolerance. That's 68 degrees Fahrenheit, pretty easy to achieve inside. So that's something that if you are calibrating equipment, you need to make sure your temperature is correct. Otherwise, everything's going to be out of whack a little bit. And you could easily figure out how much it's going to be out of whack based on the coefficient of thermal expansion. It's going to be different for different materials. It's pretty consistent for steel. You can look that up online for whatever kind of material you need. There's different accuracies for gauge blocks. Obviously, the more accurate, the more expensive it's going to be. You can see these vary from, so this would be thousandths, tenths of a thousandths. We're talking hundredths of a thousandths of an inch out here. Very, very accurate. Right? It gets into these are expensive because it's very difficult to machine things down to that level of tolerance. So these things end up being fairly expensive, especially a big set. Like if you were at a company and you were validating lots of kinds of different measuring equipment, and you need a really comprehensive set of gauge blocks, it's going to cost you quite a bit of money, and you kind of need to pay for measuring equipment. That's something you can cheap out on some things in machining and manufacturing, but you can't cheap out on measuring equipment. If you're going to spend money, spend it on measuring equipment. So gauge blocks can be stacked up. Since they're a fixed size, if you need some kind of a custom size, you can stack these things up through ringing. I highly recommend watching this video on ringing. Unfortunately, I can't just show the video due to copyright reasons, but I highly encourage you to take a look at this video here, and I'll post these slides on Canvas, and you can copy the link here. But essentially these things are machined so precisely that you can slide them next to each other, and they will adhere through molecular attraction to each other, and it feels like almost like a magnetic feel. I guess it technically is magnetic at the end of the day, but it feels like a magnet. They're not ferromagnetic, but they feel like a magnet. It's really pretty weird. So I highly encourage you watching the video. It does a good job of illustrating how to ring these things together. It's pretty cool. But essentially you can get these things to stick together because the surface is so precise between these. So accuracy versus precision. The slide's kind of a little bit out of order here, but accuracy and precision are important when it comes to measuring. So accuracy is about the maximum spread from some target. So precision is about the spread of the distribution. So for accuracy, you really want the distribution to be centered about your target. So in this case, that distribution of those different points, of those different shots, if we're shooting a BB gun at a target here, and you put all the BBs in the little 10 ring here, you're accurate, and you're also precise. You're accurate because your average is right here at the center of the target, and you're precise because the spread is relatively low. Here we are precise, but we're not accurate. Here we are accurate. If you look at the average of this distribution, you'll find the average is at the center, so we're accurate, but we're not precise. So in general, it's always better to be precise than accurate, because usually if you're precise, you can fix the accuracy. Taking the BB example, if you've got a BB gun and you shoot 100 BBs and it shoots dead on, that's great, you're done. If you've got a BB gun and shoot 100 BBs and it looks like that, then mechanically everything's good. Your aim's just a little off, so you just adjust the sight to move it from here to here. So it's usually better to be precise than accurate, because you can usually fix accuracy. Precision is the hard part. In the BB gun example, the tolerance of the BBs themselves, the tolerance of the bore of the BB gun, the air pressure tolerance, all those things matter the ability to hold the thing stable while firing, and all those things matter, and those are the hard things to fix. Adjusting the sight's the easy thing to fix. So usually precision is the key, and then accuracy you can fix. You can also be maybe accurate within samples. So you might have a process where if you repeatedly do something, like if you do something really quick, you might get a grouping here, and then if you wait a little bit and then do another grouping, it might be here, and then wait a bit and you do another grouping, it's here. That is precise within samples, but it's not overall precise, and it's not overall all accurate. So that's why it's very important to randomly, if you're going to measure something multiple times, you need to randomize the order. If you try to do things in groups and then wait and then measure things in groups, there might be factors that lead to it being precise in a group and it looks like it's accurate, but it might not really be. So it's important to do randomized measurements, randomized sampling. That's something way out of the context of this class. It's something more you'll learn about in statistics, but it's always good to randomize your samples. Allowance and tolerance. So when we start talking about things like press fits, interference fits, slit fits, things like that, we have the allowance, which is the desired difference in dimensions. So for something like a press fit, let me get allowance. The allowance is the desired amount of clearance or interference between the parts. So in this case, it's between 0.5035 and 0.5025. So a thousandth of allowance is acceptable. So we really are in a perfect world, we want a thousandth of an inch of clearance between these parts. Now we don't live in a perfect world. Whenever we try to make the block and when we try to make the shaft here, they're going to have something. They're going to have a tolerance. They're going to have a variability in their dimensions. So, and and that's going to be called out by these plus or minuses here. So that is the undesired but allowable deviation from the nominal size. So this would be the nominal size. This is the allowable variation in the nominal size. That's due to manufacturing tolerance. And again, it's like the BB gun example. It's the stiffness of the machine. It's the stiffness of the tooling you're going to use. It's how carefully you've indicated everything in, how much the 3-jaw vise on a lathe is wobbling. It's how much the material deflects as you machine it. It's so many different things that all stack up to cause parts to not be the exact same dimension. I mean, you can sit there with the same setup in a CNC machine and make 100 parts, and they're all going to vary slightly in their dimension. And it's going to look mostly like a normal distribution, but even a very controlled process, there's going to be variability. There just is. There's just so many stacked up different things that can change in any process. There's always going to be a little bit of variation, and you have to establish what's allowable and what's not, and then you have to put these two things together to determine if a fit's going to be correct or not. So as far as establishing tolerances, there's bilateral where you've got a plus or minus. Unilateral where you do a nominal and then an allowance on one side or the other. That's fairly common nowadays, and I like doing unilateral better where you have a nominal size and then you do a acceptable on the plus side or an acceptable on the minus side. If you start doing bilateral, you sort of need to, the dimension you report, like your nominal size, needs to be somewhere in the middle, and then you've got to figure out which plus or minus what are acceptable ranges, and it gets to be harder to end up calculating these things and establishing them. It's usually better to say, this is my nominal size, and this is how much bigger I can be or how much smaller I can be, depending on if it's like a shaft or a hole for a press fit. It's good to establish the nominal and then a unilateral tolerance on one side. It's easier to keep your sanity when you're trying to establish things. So you're going to probably have a normal distribution if you're making lots of parts. That shows up anytime you have a repeated random process, or it ends up looking somewhat like a normal distribution. If you're doing repeatable parts. So it's different. If you're doing mass production, this is going to happen. If you're making one-off parts, it's a little different. I've done a lot of work with design teams where we're doing one-off parts, and you have the unilateral tolerance, and you try to hit somewhere in the middle on it, and you're making one part, so you don't have a distribution. You're trying to make it within whatever the tolerance zone is. If you're manufacturing parts, you need a process that's capable of making parts within the tolerance range. It's a little bit different. So if you're doing one part, you know what your tolerance needs to be, and you can make your part within that tolerance. If you're doing mass production, you need a process that is precise enough that your parts will land within an acceptable amount of the parts will land in the tolerance zone. With a normal distribution, there's going to be tails here, and you're going to have some zone of tolerance that's going to be acceptable. And so you're going to get some out here. You're going to get some tails that are rejects. It's just going to happen unless you have an incredibly precise process or an incredibly wide tolerance. Which though I guess that could happen, and you'd have very statistically unlikely to have parts that fail. But you're going to probably have some parts that get rejected in mass production. It's just checking and making sure, doing quality control tests, doing inspection. If you're in an industry where these tails just aren't acceptable whatsoever, you might have to end up checking every part. Some industries, if it's very unlikely to get a part that's out here in the tail, you might just check a certain however many runs and assume it's going to be okay, or just there's an allowance for a few parts that are out of spec. Again, depends on what industry you're in. Now I'm not going to update Apple's software. So there's different standards for tolerances. ANSI is one, the American National Standards Institute. Here in the U.S., we use the ANSI standards for a lot of things. They vary from Class 1, which is a loose fit, large allowance, which you guys can do the math here. But for a 1-inch diameter shaft, that'd be 2.5 thousandths clearance. So if you take a shaft and put a collar on it that's 2.5 thousandths bigger, it's a pretty loose fit. It will rattle around in there pretty much. A snug fit, there is 0 allowance. So that is very hard to do in practice. So we'll talk about the tolerance on that in a second. But a snug fit has a 0 allowance, and the tolerance for it is going to be really small. We're talking tolerances down in tenths of a thousandths of an inch. And so for a snug fit, you really want at most about a 1/2 of an inch for something like it's an inch diameter, and it's really hard to get the tolerances down to that on manufacturing equipment, especially for large runs. You need very precise equipment. For this ringing fit, you need incredibly good tolerance or allowance. You need an average interference around 0. And then it gets up to interference fits here, like a Class 8 interference we're looking at, and interference, not an allowance, of 1,000th per inch. So for a 1-inch bar, you're talking about having 1,000th of an inch of interference in that. And then for 2-inch, you need 2,000ths of an inch. So you're going to have bearing presses that are going to be somewhere in here, like this Class 8 fit. These parts, when they're pressed together, they're going to be stuck together pretty good. And if you're pressing a bearing into a bore or something, you might actually seize up a bearing with a Class 8 fit. Depends on what's recommended by the bearing manufacturer. But I've seen bad press fits where on an inch or 2 diameter part, there's 2,000ths of press that'll ruin a bearing. So you got to be very careful when you're pressing things like bearings in. So that's why it's important to establish what class is acceptable and then set up your tolerances accordingly. So a couple examples here. So this would be like a 3/4 inch shaft. We want a Class 2 fit. So for this, this is going to allow these parts to run versus each other at around 600 RPM or higher, and bear pressures of over 600 PSI. So this would be like a bearing clearance essentially. So this is a shaft in a hole or shaft in a bushing. So it's fairly a little tighter than this loose fit here. There's enough room for these parts to move with respect to each other, but not have a whole lot of play in them too. So for a Class 2 for a 3/4 inch shaft, we have an allowance of this. So this is 1,000th plus 1.6 of a thousandth. So that's not a lot, right? We need just over 1,000th of an inch clearance in this. That's our allowance. And then we're going to have a tolerance of just over 1,000th too. So how these things stack up, I'll show you in a second. But we just don't have a lot of room to work with here. So how we work this out, sorry, I'll turn my phone off. So how we work this out, we have our nominal diameter for our hole is where we'll start. So that's our nominal diameter for the hole. We're going to add our tolerance to that to get our maximum size for the hole. So this would be, I've got a kind of a close-up, so if you zoomed in right here, that's what this would be right here. So we've got the nominal size of the hole that's sitting out here at 3/4 of an inch. We're going to have the tolerance, allowable tolerance on top of that. So we're going to add on the tolerance to our nominal hole size, and we get the maximum permissible size for the hole there. Then we've got the shaft. So for the shaft, we're going to take the nominal hole size and subtract off the allowance to get our nominal shaft size. So if we built the hole exactly to the spec, it'd be 3/4 of an inch, and if we built the shaft exactly to the allowance, it'd be this 0.74884 of an inch. And this, so in a perfect world, we'd make the hole this size, we make the shaft this size, we have our allowance between them, everything is great. Again, we can't build these things exactly to the tolerance, so what we're going to do here is say it's going to be an acceptable hole if it varies from 0.75 to 0.7118. And obviously the gap between these is going to increase, right? It's going to almost double in size. Actually, yeah, it's going to almost double in size. It's going to over double in size because the tolerance is higher than the allowance. The shaft, likewise, right, we're not going to be able to manufacture it at exactly 0.74884 inches because we're talking about on a mill or a lathe, we can do this. We may be able to do 1/2 of a tenth on a mill or a lathe. We're not doing 100ths of an inch on a mill or a lathe. So we need to make this thing somewhere somewhere in this zone here. So we subtract the tolerance off the nominal. This is where we need to make the shaft. So if the hole is in here and the shaft is in here, we're going to have at least the allowance that we need, that 0.00116, and the allowance plus the stack of the tolerances, we're going to be okay. So essentially the clearance can be anywhere from this to this. So it's almost 3 times, actually more than 3 times. So there's quite a lot of wiggle room in this. Now, usually the closer you are to the allowance, the better. It's going to work better. So you really want to try to get to these nominals. If I was manufacturing this in a one-off thing for like a, just a one-off project for a student design team or something like that, I'm probably going to shoot for 0.7505. I could probably hit that plus or minus that half thousandth on a pretty good day on a lathe. And then on the shaft, gosh, it's going to be kind of 0.748 is probably what I would try to shoot for on that. I might try to shoot for 748. I don't know. It's probably what I'd have to hit, but 748. And that'd give me about 1,000. What, 2.5 thousandths. I don't know. We might get a little tighter than that. I don't know. You kind of have to. You're not able to hit this kind of precision, so you need to sort of pick something to shoot for if you're doing one-off. If you're doing a mass production run, you really want the average part to be somewhere right in the middle of this, and then you've got your normal distribution that's going to, you really want the mean of that to be in the center, and your processes need to be accurate enough or precise enough that they can be within the tolerance range here. For an interference fit, it works out a little different. So same 3/4 inch shaft, we're going to do a class 8 interference. So this is 1,000th for every inch. So we have 3/4 of an inch, so we have 3/4 of a thousandth. So we've got 70, so 3/4 of a thousandth of an inch out here, or 7.5 tenths of a thousandth of an inch. I don't think this is better in metric. It's just as bad in metric. The numbers, I mean, it always ends up being a whole bunch of decimal places regardless of what unit system you're doing. So we need 3/4 of a thousandth of an inch here. Tolerance is also way down here. So there's not a lot of tolerance for press fits usually. Press fits, a little too much interference can cause problems. Not enough interference means it's not a press fit. So there's just not a lot of wiggle room on press fits. So in this case, what we need is the shaft to be bigger than the hole, so we have interference. So the easiest way to establish this is start with the nominal hole size, so 3/4 of an inch. So 3/4 of an inch, that's our nominal hole size. Our acceptable tolerance on the hole is that 0.00055. So this is our tolerance range for the hole. So it can be nominally, it's acceptable up to this size. Okay, then the minimum shaft size. So actually, let's go nominal shaft size. So the nominal shaft size is going to be the whole nominal size. So that's going to be the whole nominal size plus the interference, which is this 3/4 of a thousandth here. So we're going to add the interference, to our nominal hole size, and that's going to be our nominal shaft size. So in a perfect world, we'd make the hole this big, the shaft this big. We'd have our interference, or specified interference, and we could press these things together, and they'd stick together. They wouldn't come apart unless there was a lot of force on them, and it wouldn't damage, the shaft wouldn't be damaged, or the hole wouldn't be damaged by pressing these things together. So this would be a good fit. But again, tolerances, right? So we need to add the tolerance onto the hole. We need to add the tolerance on to the shaft. So the worst case press would be from here to here, and that's going to be the interference plus the tolerance, be the max case. So add these two together, and that's going to give you the maximum amount of difference. It would be 1.3 thousandths of an inch would be the worst case scenario press. And then on the other side of things, it'd be here. That'd be the gap there, and that would be 2/10 of an inch. So it's a big range, right? So it's about 0.0013 inch on one side to 0.0002 inch would be your range for your press fits. Big range. If you're making a one-off part, you probably want this, just from personal experience on something this size, You really want something around more like 5/10 of a thousandth of an inch for something like this. For things like bearings, for a 3/4 inch diameter bearing, if you put a thousandth press fit on it, it's probably going to seize. So you really on this, you probably want to be closer to the low. So it depends on what you're doing. If you're trying to lock two parts together, they're not bearings, you just really want to smash them together and have them together, then yeah, sure, be on the higher side of that. Again, if you're doing mass production, it's all distribution. So you really want the distribution of this to be, I'm drawing terrible normal distributions here. There's a better normal distribution. Right, you're going to have, you want your mean somewhere in the middle here, and you want to make sure your process are, they're tight enough to then get you within that tolerance window here. ISO has its own set standards, of course, the International Standards Organization. It's different than our standards here. You'll run into both out in the industry, so you see both. ANSI you mostly see here in the U.S., but you run into ISO standards too. So it's a frustrating thing, but you know, it is what it is. So I'm not as familiar with the ISO standards. There's 3 classes: clearance, transition, there's interference fits, there's numbers and letters. Again, this is something you'd have to look up the specific standards, which you could find online if you needed to. Metrology, the science of measurement. Talk a little bit about, mainly about mechanical measurements today, internal and external dimensions. There's all sorts of other ways of measuring things, optical measurements, pneumatic, which I've never seen. I'll have a slide on that. But surface roughness, that's important too for calling out surface roughness and validating it. Non-destructive inspection and testing too. As far as mechanical measurements go, sort of the first thing you need is a machinist rule, essentially a fancy ruler. These can have different resolutions. 64th of an inch is common. 100th of an inch is common too. I've got a 24-inch 100th of an inch Brown and Sharp rule. That's sort of my go-to rule for measuring things. It gets kind of hard to see 100th of an inch, so you might need a magnifying glass to actually see down to that. That's 10 thousandths. It's pretty small. It's twice the width of a human hair. Actually, no, that's about a human hair is about 100th of an inch. So we're talking seeing 100th of an inch, which means there's little bitty markings here at 100th of an inch. So you also see tenths is real common. This would be the tenth one. Tenths ones are pretty common, and then you can see the hundredths on this one too. And then you can see the ones here that are in 64. So in engineering, we pretty well in manufacturing, we do everything in tenths. That's right. It's just the sweet spot for manufacturing is right around 1/10 of an inch. So we like to measure things in thousandths of an inch. So so it makes sense to do tens, hundreds, one. You know, it doesn't really make sense to do fractional inch. It's just easier to do everything in tenths. So sorry, I keep saying tenths, in thousandths of an inch. We do things in thousandths of an inch. You'll see these are much more common. That's a pretty common rule. There's all sorts of different lengths of these: 6-inch, 10-inch. I got a 24-inch one that I use for measuring all sorts of stuff. They're expensive for what they are for a ruler, but you need to buy expensive measuring equipment. Again, don't cheap out on measuring equipment. It's a really silly thing to do. Micrometer for measuring external dimensions, external diameters, things like that. So they usually have an inch range of measurement, which means that this goes from 0 to an inch on most of these. So if you need to measure something that's 1.5 inches, you need one that's bigger than, there's a 0 to 1, there'll be a 1 to 2, there'll be a 2 to 3, and so on. It gets up to 5 to 6 inches, 6 to 7 inches. They start to get really expensive at that point. A 0 to 1, it's one of the first pieces of measuring equipment you need to buy is a 0 to 1 micrometer. Like I've got a 0 to 1, a 1 to 2, and a 2 to 3. Anything past that, it gets very expensive very quick, especially for good equipment. There's bigger ones, but they get a lot more expensive. These are accurate and can measure down to tenths of a thousandths of an inch. So you basically put your part in here, you turn the thimble here until it contacts the part. These will usually have some kind of a torque limiting device to make sure that you have the right torque on it. If you really tighten this thimble down, you can actually squish the thing you're measuring and distort your measurement. So these will usually have some little thumb wheel back here that gets you to the right torque for your measurement. When you're measuring tenths of a thousandth of an inch, it matters. It can matter quite a lot actually with how tight you have this thing torqued. So you're going to have your base measurement, which for a 0 to 1 inch, the base measurement's 0, and then these measurements here. So this would be 0, this would be a tenth, this would be 2 tenths. And then your wheel here is usually going to be in 25 thousandths. So you've got 4 revolutions of that will get you from 1/10 to 2/10. And so you look at this mark here, and that'll give you, so this, you take your base, which for a 0 to 1 would be 0, you count your tenths, and then you count your thousandths here, 0 to 25, and then you need to know if you're at the 0 to 25, 25 to 50, 50 to 75, 75 to 100 here. That gets you down to thousandths of an inch. And then to do tenths, there's this other little scale here that you find the mark that is closest aligned to the 100th mark. This is not something I can explain very well in this format. It's something in the manufacturing lab we'll cover. So it's something we're going to figure out for those of you that haven't had that lab yet. We'll figure out how to do that online. We'll probably do a video of us showing you how to set this equipment up. But again, I'll explain the basics here, but you really need to see somebody measuring these. Once you've done it a few times, it's second nature. It's really easy to measure with these things. And it's a pretty simple device for measuring down to a tenth of a thousandth of an inch. There's different little anvils you can screw in here for measuring different things. You need to spend money on these. Your measuring equipment's the most important thing out there. These are all examples of Starrett equipment. Starrett's a good brand. Brown & Sharp's a good brand. Mitutoyo is a good brand. There's lots of good brands out there. There's different people have different preferences, but you really need to buy good measuring equipment. So here's a few different ones. Little micrometers, external mics, and different anvil designs. A big frame here. Obviously, this is going to get more expensive here. There's digital ones. I'm not a big fan of digital measuring equipment. I know it's a little easier, but for stuff like this, I like buying expensive mechanical equipment that if you take care of it, it will last forever. I mean, there's no really, unless you do something bad to these things or let them rust away, they don't get damaged. So these things have little electronic gizmos in them, and I have a lot of experience with electronic gizmos as a mechanical engineer. I've done a lot of circuit board design and fabrication, and there's just a lot more things that can go wrong in these. So they're more convenient, but if you really want to buy something nice for the long haul, I really recommend buying mechanical measuring equipment. I know there's something very satisfying about this, and after a little practice, it's super easy to read these. Dial calipers. This probably should have been first, because if you're going to buy one thing to measure stuff in mechanical engineering, a good set of calipers is really your first stop. There's vernier and dial. You don't see vernier that much anymore, thankfully, because they're a giant pain to read. But they're very simple. Dial caliper, that's what literally almost everybody uses, is some dial caliper or digital caliper nowadays. A very good quality dial caliper is probably the most basic piece of measuring equipment you need. I guess the rule is the first one, and then a dial caliper. So again, we'll probably do, if you have the lab for this, great. If not, we'll do a video on measuring different things with these. But essentially you've got a gauge here that'll be tenths of an inch usually, and then this will be in thousandths. So you put them, so this will usually have 100 thousandths going around. So you take the tenths that you read off the gauge, and then you measure the hundredths, measure the tenths, and you take the tenths plus, you take the tenth of an inch plus the thousandths you count, and you get the dimensions. Again, this needs a video by itself to show you how to use these, so we'll get that for you. But like everything else, buy good calipers. There's lots of different brands out there. There's a lot of really junky brands that don't last. So there's not a lot of companies that make very good high quality calipers. The ones I use, I prefer Brown & Sharp, but Starrett's a good brand. Mitutoyo is a good brand. There's other good brands out there too. You have to do a little research, but buy good calipers. There's also digital calipers. They're convenient. I do not trust, unless they're very, very expensive digital calipers, I wouldn't trust them for anything I cared about. So I'm sure there's very good high-end ones from Starrett and Brown & Sharp and Mitutoyo that are digital and really convenient. And yeah, you can switch between metric and inches, and it works great. Really like mechanical on these. Vernier, I don't even know how to use anymore. I'm sure I could figure it out, but you just don't see vernier that much. If the world ended, then these might be useful, but these are a little more finicky and can there's a little rack and pinion inside these that has to be kept clean, and these have to be you have to maintain them. You can't drop them. You can't get them wet and get them all rusty. You gotta keep your equipment clean and maintained well, but these will last forever if you take care of them. Dropping them is usually how these things die, is getting dropped. So don't drop your calipers. Don't put them in a spot where they can be dropped. You're going to be measuring down to 1/1000th of an inch or so with these. They make big ones, but 6-inch and 9-inch are pretty common. 12, it starts to get expensive. 24, it's nice to have a 24-inch set of calipers, but it gets really pricey for one you actually want to buy. And I can't imagine how much a 72-inch caliper is. I mean, it'd be a lot, many thousands of dollars. You know, a good 6-inch caliper might be $150. But again, if you don't drop it, you'll have it forever. Angle measures, there's bevel protractors. You can set up a little custom station where you've got a sine bar on ground pins here, and you use gauge blocks, and then you run a dial indicator and check. So you have to do a little bit of math on this to see what the run out to stack this all up so you get the right angle here, and then do your run out from one end to the other on it. But there's lots of different ways to measure angles. It's usually more frustrating than anything else, measuring angles. So measuring it like this works pretty well, where you've got a sine bar that you can put at a specific angle using gauge blocks, and then run a dial indicator over it to see what the tolerance is. Angles are a pain to manufacture, and they're a pain to measure. Internal diameter, this is frustrating. External diameters are pretty easy. You just use micrometers and things work great. Measuring internal bores, you can use these telescoping gauges, which take a lot of practice to get correct. You essentially, there's a little thumb screw that locks these things in, so you push these things in by hand with the thumb screw out. You tighten the thumb screw, that locks them in. You put it in the bore, you release the thumb screw, these things are spring-loaded and pop out. Then you tighten the thumb screw, pull this thing out, and measure it with a micrometer. And you can see there's lots of places for this to go wrong. So it takes a lot of practice and a very good set of these to be able to get good dimensions using telescoping gauges. I have screwed up a lot of parts with telescoping gauges before. So just like everything else, I know these are a stupid, simple mechanical thing, but buy good telescoping gauges. They also make bore gauges. This would be an incredibly expensive piece of equipment here. Bore gauges usually are, for measuring something like cylinder bores and engines. It's an expensive piece of equipment. So they do make some micrometers that have pins that you can measure internal bores with, but it's pretty dedicated, pretty expensive. So internal diameters are a pain. Usually people try to do it with these, and again, if you practice with it, you can do a good job. But it's real easy to screw it up using these telescoping gauges too. That's something that's worth practicing a lot, and double checking. I always double check a measurement with these by using the inside jaws on dial calipers. I always do a sanity test on my measurements with a telescoping gauge to make sure it's not off by a lot. This will usually get within 1/1000th or two on the inside diameter. With a little technique, you can do a pretty good job measuring internal bores with these. But these jaws are usually pretty sharp, and they'll actually cut into material, and that might affect your dimensions too. So takes a little bit of practice with this to get good measurements. CMMs, these are coordinate measuring machines for measuring arbitrary things very precisely. These are really fun, really kind of amazing and huge time savers. They're used a lot for automated inspection of parts. So essentially you use a little probe here. This probe will contact you, basically gently run the probe into the part, and the machine will record where the probe contacted the part. These things can be accurate down to 1/10 of a thousandth of an inch or so. And then this probe is usually mostly a sphere here, and so you can contact it pretty well everywhere but on the shaft of this thing. And then this will be on a head that you can rotate. This one would probably be 3 axes, but you can get ones that can rotate around in 5 axes. This one would be one you'd manually move around. So this would have these little switches actually are for the vacuum slides. So this will be on very precisely machined slides, and then sorry, not vacuum, they'll use the air pressure in here and to create air bearings to allow this thing to move very nicely and smoothly. Obviously this has to be very precise for you to have good dimensions. They'll measure the distance you've moved this way, the distance you've moved this way, the distance you've moved this way, and then the probe will detect where that you've contacted and where you contacted on the sphere. And from the measurements of the slides and the measurements from the probe, it can figure out where the point you touched is in three-dimensional space. So this one would be manual. You'd move it all around. They make big CNC ones that automatically can measure. They make these for CNC milling machines and turning centers, where you can actually inspect the parts as you're manufacturing. That's pretty cool, pretty sophisticated. They make big, gigantic ones. Obviously these are going to get expensive. You know, small one's pretty expensive. You get into this scale and you get into a whole world of expense. So there's all sorts of interesting optical scanning tools out there now. I haven't played around a lot with these. They're more common now than they were 10, 20 years ago when I did more stuff in the industry. But there was lots of interesting options on scanning, contouring, bringing parts in to CAD software. So fixed gauges, we talked about the gauge blocks. There's go, no-go gauges. These are common in things like rifle bores. There's go and no-go gauges to make sure you've machined the chamber correctly, where if one gauge is supposed to go in, another gauge is not supposed to go in. So if the first gauge, if the go gauge doesn't go in, then it's too small. If the no-go gauge does go in, it's too big. And if the go gauge goes and the no-go gauge doesn't go, you're bracketed in that tolerance band and things are okay. These are very custom to whatever the application is. There's thread gauges. This is a go, no-go thread gauge where one thread should go in, the other thread should not go in. So this is a snap gauge where you set it to a specific dimension, and then you basically pull lever, put this on the part, release the lever, and you can see what tolerance you're in there. These are pretty custom to the different applications things you're trying to measure. Form gauges for checking threads. You almost always use a thread gauge to measure like thread pitch. If you just found some random nut or bolt and wanted to figure out what thread it was, you usually get a set of thread gauges. There'll be a metric one, there'll be an SAE one. This would be a metric one. It's a module here. This would be an SAE radius gauge here. It's just a comparator. You'll hold it up, and for thread gauges it's pretty simple. You might want to check if you truly have no idea what something is, if it's metric or SAE. It's probably good to check it with both and see which thread matches the most. Some of these can be pretty close. Usually from markings on the bolt or head of a bolt or something, you can figure out what the actual size is on it, though. This would be for checking corner radii. It's very hard to check a corner radius, so this is something you could hold up and verify corner radii, or at least bracket it between two different measurements. They also make feeler gauges too in different thicknesses. That's something that if you want to measure a gap very precisely, like doing valve lash in an engine, they make feeler gauges, which you might have a set that goes anywhere from, I don't know, 1/10 of an inch. Well, that'd be pretty big, but 40 or 50 thousandths down to 1/1000th of an inch, down to 1/2 of a 1/1000th of an inch. Deviation gauges, dial indicators. So this is very useful in machining, especially if you have a manual milling or turning machine where you don't have a digital readout. This is what you can use to measure. You can measure all sorts of things. You can measure run out. You can measure how much your axes are moving. They're very, very useful for lots of different applications. So in addition to your rule, your calipers, your micrometer, you need a good dial indicator. This one's going to measure in thousandths of an inch. You can get 1/10 of a thousandth of an inch ones too. You can get different ranges. Again, you need to buy good ones of these. This is a Brown and Sharp. Most of my measuring equipment, I try to buy Brown and Sharp. It's expensive, but it is good. Starrett's good. Mitutoyo's good. There's other good companies you can research, but buy good equipment. LVDT, I've never seen one of these things before, but this is for measuring precise translations. We use a rotary variable differential transformer for doing measuring angular position in electric motors. It's a pretty common way, a resolver for measuring angular position. Same kind of concept. In this case, we're essentially, we've got a winding here, and we have two windings, one moving winding and one fixed winding, and we can measure how much something moves by the current induced in the windings. This will be used for measuring like the variation in a surface. Optical techniques, there's laser interferometers, there's optical flat, which I've never used before, optical comparators, which you'll see at some places. There's all sorts of different optical methods of measuring. These are more specific to certain industries. I don't have a lot of experience to talk about in this. Air gauge, this is for measuring bore size. So in this case, you're injecting air into a bore and measuring the volume flowing and the pressure drop, so that you can measure down to maybe 1/10 of a thousandth of an inch, and also check out of roundness. If it's something out of round, you might have more air leaking. Surface roughness. So there's the dimensions that you measure, but there's also the surface finish too, and it's kind of hard to distinguish from these things. But you might have something that has a very accurate dimension that you'd measure, but the surface is very rough, and so you're really only measuring the peaks here. You're not actually measuring down in the valleys here. So you usually specify surface finish, surface roughness separate from the actual dimensionality of a part, because again, if you put calipers on this thing, your calipers are going to rest here, and you're not really measuring at all what's going on at the lower peaks here. So you really need both. You need the nominal dimensions. You also need to specify the roughness, which is the variation in this surface here. So this is going to be variable depending on the manufacturing process you use. So we usually use some kind of average on this. So we take some kind of a machine, we move it over the surface, we measure the deflection, and then we calculate some metric that is the surface roughness. So there's lots of different ways of doing that. Root mean square is pretty common. You could just taking the sample average like that, I don't know how accurate it'd be. You've got pluses and minuses, so might not be very good. But root mean square gives you a pretty good number on it. You can estimate it for turn parts with your cutter radius. So feed rate squared over 8 cut times the corner radius. You can estimate it. You have to know your corner radius of your tool, which you probably know, and you can know your feed rate probably too. So you could estimate it pretty well. You can actually get pretty good surface finish on turning. We'll talk more about that later on in the class. But so these are usually you can measure them. In a lot of cases, you'll just use a comparator, which I don't have a slide for that, but a comparator will be a little set of samples of different surface finishes, and you just hold your part up and optically, visually compare your part to the comparator and see if the surface finish looks good. I mean, it's not a measurement, but it can get you pretty close. So you see a lot of those comparators. And a lot of this, the surface finish, you're not going to sit there and measure every part unless you're doing something very, 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 very sophisticated, very spooky. So you don't see a lot of that. So most of the time you'll make a few parts, make sure they're good, check quality on a few parts, and assume that the rest of them are good based on the sample that you measured. Surface roughness, direct measurement. Comparison techniques, pretty common. We use a comparator. Non-contact, I'm not very familiar with. There's some other methods too that are fancier methods that I'm sure if you're in that manufacturing quality control industry, you'll learn more about those. But the basic ones are you're directly measuring it and then using a comparator to compare it. So that's it for today. So thank you all, and I'll provide another lecture on Thursday of this week. So thank you.